I'm Xingjian Zhang from the University of Hong Kong, and it is my great pleasure to be here to introduce our recent results on this what we think very interesting topic. So the title of my talk is Succinct Perfect Zero Knowledge for MIP Star. First of all, I would like to maybe put some remarks here. So this is a work with Professor Hong Haofu from the University from Concordia. And you can access an earlier version of our result on arXiv. But something to be mentioned here is that our earlier version is so what I shall later introduce. So it is only perfect zero knowledge against honest verifiers. And now in an upcoming new version, so which we hope to post on arXiv in about maybe in mid-September. So we have this perfect zero knowledge against these honest verifiers, and we are lucky to have Kieran Mastel from the University of Waterloo to our rescue. Okay, so the talk, my talk today will be organized as follows. So first, I will introduce the background. So basically, I will introduce the two notions in this title. So one is this MIP star, and another is this zero knowledge proof. And then I will briefly explain our main result, so which is this title. And then I will give a black box outlook and also some explanation of our results. And then if you are still interested in how we do it, then for the last part, I will give you some knowledge of this zero knowledge result. So it will be a super high-level proof sketch. Okay, so now let's get started. So first, the background and the main result. Okay, so as some of you may have heard of, one of the biggest breakthrough in 2020 is this MIP star equals to RE result. So what does it mean? So MIP star represents the multi-prover interactive proofs using entanglement. So the star represents entanglement. And this RE represents the recursive enumerable languages. So why is this result so important? So one aspect is that this RE complexity class, it is super large. So the RE complete problem is the famous halting problem. So it represents all the Turing machines that halt in a finite number of steps. So the yes instance is that this Turing machine will halt in finite steps. And this problem is explain that so someone after Turing. So this halting problem is a famous undecidable problem. So there is no universal Turing machine that. What is this MIP star? So roughly speaking, the MIP star can be seen as a sequence of nonlocal games. So here is this very So here is this nonlocal game. So we are already very familiar with it. So we have this referee. The referee will ask some questions to nonlocal players X and Y. So the nonlocal players may share entanglement at first, and they will respond answers A and B to this referee. One thing is that although the players can share entanglement, they cannot communicate with each other during the game. And afterwards, this referee will check their answers with respect to a predetermined relationship. So to check whether this function, the function of x, y, a, b equals to 1, whether this relation is satisfied. If it is satisfied, then the referee says that the players win this game. Okay, so this is the nonlocal game, and now we put it in the language of into this MIP star, the interactive proofs. So the referee is now seen as a classical verifier because he asks the classical questions and receive classical answers. One thing to be reminded here is that this verifier, he only has bounded classical computation power. On the other hand, the players, which we now call the provers, so they can share entanglement, they can be malicious, they can be all-powerful in their own computational power, but they cannot communicate. So that is the only restriction. And now these questions and answers during the nonlocal game is seen as the interactions. And finally, the winning of the game is that the provers somehow show the truth of a statement to the verifier. Okay, now let's have a some flavor of why you can use this MIP star to show that it equals to RE. So how it encodes this halting instance so that a Turing machine can halt into this MIP star protocol. So now we consider not just one single nonlocal game, but a sequence of games. So this sequence of games will require a growing amount of entanglement to win perfectly. So if this Turing machine will halt at some step, then this nonlocal game indexed by n will, so the provers can win this game perfectly. On the other hand, if this Turing machine cannot halt, then for every nonlocal game in this sequence, there is an upper bound on the winning probability. And so we call this S parameter. So it actually can be a function in terms of this game index. So this S is called the soundness parameter in this MIP star protocol. So roughly speaking, what this MIP star equals to RE result shows that there exists a sequence of nonlocal games that is polynomially in a polynomial size in terms of this input instance. So the input instance is the description of a Turing machine. So this is possible, and in particular, the soundness parameter is actually a constant. Okay, so this is MIP star. So an MIP star, so it is an interactive proof. So the reason people study these interactive proof systems actually originates from a cryptography aspect. That is, you can actually use interactions to do zero knowledge. So here is a one zero knowledge statement. So Gru says that he can prove that he is able to steal the moon without actually doing this task to you. So without showing anything beyond this mere knowledge to the verifier. Now let's have some maybe some math here. So let's say here let's consider this interactive protocol. So we have so the upper part is the prover and the lower part is the verifier. So they do the interactions during this interactive proof system. What the verifier has is the input of this statement, and also the verifier may have some additional randomness themselves. And the prover, so they do interactions, and the prover somehow shows the truth of this statement to the verifier. Now you can consider that from the viewpoint of this verifier, so what they see is some dialogues, some interactions, X and A. Now let's consider another simulator. So this simulator is probabilistic and run in a polynomial time in terms of the input size. So the simulator has this input and this Z, but actually the simulator does not know how to prove this statement themselves. But somehow the simulator can simulate the entire dialogue. So from the viewpoint of the verifier, what the verifier sees is the same distribution. Then if this is possible, then we see that this is perfect zero knowledge. And now you can also have some variance or maybe relaxation of this zero knowledge idea. So you can have statistical zero knowledge. So the prover generates a distribution that is close to this ideal to the actual case, or maybe the computational zero knowledge, which means that so the verifier cannot distinguish these two distributions in a polynomial time. And in general, so actually we need to show that this is zero knowledge against a dishonest verifier, which means that this dishonest verifier may deviate from the honest implementation and tries to steal your knowledge about how you prove this statement. So we actually want to, in most cases, we are interested in how to show the zero knowledge against a dishonest verifier. Okay, so now move on to our questions. So, so what motivates us to study this problem? So the first thing is that can we do perfect zero knowledge for MIP star, particularly for the proof of this RE complete problem, the halting problem? So this has been answered in a confirmative way last year by Mastel and Slofstra. So this is yes. And the second thing we want to ask is how succinct this proof can be. So the succinctness is in terms of the communication cost, so and also the verification time by the verifier. And why do we care this problem? So of course, it is an interesting problem mathematically. And another thing is that as first Kilian shows that you can use this to hinder the proofs from cheating physically. And also, it is the first step you want to do some useful applications in practice. And our result is like this. So, so the last column is our result. So we actually have a two-prover system and in a single round. So the provers can do this. So this is in the simulated case. And we have perfect completeness and a constant soundness. So these are optimal numbers. And compared to the result by Slofstra and Mastel, we show that you can improve this polynomial time communication into a polylog communication cost. And as a comparison, here I also give you the result for the classical case. You can see that our result is somehow very close to this optimal possible case, despite this polylog. So we have an additional poly, not just log. And here is a black box outlook. So first, our result for this polylog answer case is actually an AM*2 protocol. So it is a two-prover quantum-free game with constant size questions. Another thing I didn't mention in the last slide is that the verification time is actually a polynomial time, and we show that this is somehow necessary. So this is not the same as in the usual practice in classical case, because in classical case, people are usually interested in the succinctness requires a polylog. And finally, about this communication cost for MIP star. So Natarajan and Zhang showed that actually you must require a log type length communication for the MIP star protocol. And they also show a result that is very close to this, despite that the soundness will shrink to 0 in the asymptotic case. And this problem is actually related to the game version of quantum TCP, but the difference here is that for the game version of quantum TCP, you do not need to do this MIP star for the halting problem, but just for a QMA complete problem. So this is still remains open. And finally, I will explain the super high-level proof sketch very quickly. So this is the starting point. So we have a sequence of games that encodes the halting problem, and we just explain the logic behind this. But the problem here is that the protocol you may think of may take a too long question and too long answers, so the verifier cannot actually do that. So for this purpose, we will do several steps. So the first step is the so-called question reduction. So the essential idea is that to let the provers sample the questions themselves. So in this way, you can exponentially reduce the question length. But so one caveat in the question reduction is that the completeness soundness gap will drop to 0. So for this purpose, we will use parallel repetition to recover this constant soundness. And another step is that we will use the probabilistic checkable proofs to do the answer reduction. And this is also allows you to reduce the answer length exponentially. So in this way, you can have the short answers. But here, another problem is that in answer reduction, you actually need to have Alice and Bob together to complete this proof. But we know that in nonlocal game, they cannot communicate with each other. So for this purpose, we introduce another step that is called oracularization. So in some cases, one player will get both questions in the original protocol, and somehow in this way, this oracularized prover can calculate the entire PCP. So now this is the final slide. So we upgrade the original MIP star protocol into a succinct perfect zero knowledge MIP star protocol. And here is the recipe. So we start from MIP star protocol, which has constant question length and polylog answer length. So it is not perfect. It is not zero knowledge as a step. So this is our final target. So in the middle, we will do perfect zero knowledge using the Barrington's branching program and some randomized tabular technique to turn it into a perfect zero knowledge MIP star protocol with polynomial long questions and answers. And if we have this description, we can then calculate the needed size for you to do all the stuff, for you to the number of times you need to do this recursive question reduction and answer reduction. Then you can, at the end, you can output this desirable protocol. One thing to mention is that this oracularization procedure is very, so it is annoying because of this oracularization problem, because in a dishonest verifier case, this dishonest verifier may ask more questions to the oracularized provers, and these provers cannot see this possibility, and we want to show it is also zero knowledge against such dishonest verifier. And for this reason, we now do not have a black box reduction to do this succinct zero knowledge, and we think this might be an interesting open question. And another thing to say is that if you just consider a honest verifier case, then a black box reduction is possible. Okay, so that is all for my talk, and thank you for your attention.
Thanks a lot, Xingjian. So there's time for some questions.
Thank you for the very nice talk. Can you say again what is the intuition behind requiring the Barrington theorem behind using the branching program?
Can you speak a little bit louder?
Can you say again what is the intuition behind using the branching program at the very end?
Yes, so here the intuition here is that you first using this Barrington's branching program to describe the things in terms of these cycles in the permutation group. And then in this way, you can add randomizers to this output of the branching program. And it is like that you somehow use the trick that you do if you are familiar with the zero knowledge proof for the MIP complete problem, then you can use some kind of randomizers to hide your knowledge in terms of this. So that is, we have a randomized tabular. So the idea is that now, originally you have a description of the nonlocal game, but now you add more questions. And the knowledge is actually encoded in this very large question. But in the way that the verifier asks the questions, they can only ask a part of this long question, so the knowledge is kind of hidden.
Thank you so much.
Yeah, thank you.
Thank you for the talk. And I say to prove zero knowledge, there exists a simulation function that can simulate the verifier. So can the simulation function make use of these reductions, or it just guess randomly?
Yeah, thank you. Yeah, so this is actually a very good question. So this is related to the final part, so this black box reduction problem. So at this moment, we cannot show I think for the question reduction, answer reduction, and also the parallel repetition, you can actually show a black box kind of zero knowledge reduction for these steps. But the only remaining part is that at this moment, we do not know how to do this job for the oracularization part. And for that part, we need to open the box and see how it works.
But you regard to a perfect zero knowledge. So there exists a simulation function, but but it has no relation with this reduction function.
What do you mean by this relation with the reduction?
I mean, in order to prove zero knowledge, there have to exist a simulation function. Mm-hmm. So do you find this function?
Oh, yes, we found this simulator. We construct it very explicitly.
And the simulation function you found has nothing to do with the reduction?
I think that is, yes, it is in terms of the, actually it is we actually do this zero knowledge simulator at the beginning. So it is like we need to calculate the number of steps for you to do all these reductions. And this simulator actually needs that as an input and for the construction. So it is like you know how you do all the steps, and then with this whole description, you have this simulator.
Oh, okay, I understand. Thank you.
Okay, thank you.